Hello everyone, my name is Dr. Venkat, professor in the Department of ECE, Godavari Institute of Engineering and Technology. In this lecture video, we are going to discuss about discrete Fourier transform, which is a very important concept in the field of digital signal processing. Now, before introducing to DFT, let me quickly take you through the objectives of this session. The objectives are derivation of the DFT. We'll see how DFT is mathematically derived, and then we'll see the relation between DFT and discrete time Fourier transform and what are the basic differences between them. And then we try to solve a couple of problems on DFT and IDFT. All right. So let me take you through. First of all, what is DTFT? Discrete time Fourier transform. We all know that Fourier transform is used to represent the frequency domain representation of non-periodic signals. And discrete time represents it's basically Fourier transform of a discrete time signal. So you can see a discrete time signal here, x of n. So if you recollect the definition of discrete time signal, x of n, amplitudes are only defined at specific instants of time. Alright? So discrete time Fourier transform represents the Fourier transform of a discrete time signal. As defined, you can see in the analysis equation, it is x of omega. Let me quickly take the pen. You can see here, this is the definition of DTFT. You can see the input is x of n. The input is x of n and it is multiplied with e power minus j omega n and perform summation over minus infinity to plus infinity. That basically gives you the Fourier transform of a discrete time signal. Now, one major problem with this DTFT is that even though the input signal x of n is discrete in nature, the spectrum of the signal is not discrete in nature. It is still continuous in nature. And such signals do not have a practical application. So we cannot practically implement them on a digital computer or a digital signal processor. So DSP is not possible. Digital signal processing is not possible for such signals. So what is the alternate solution? DTFT is fine. It represents the Fourier transform of a discrete time signal, but the problem is it is continuous in nature. So what we can do, one possible solution is that we can limit the extent of the summation. As you see here, the summation is from minus infinity to plus infinity. You see here, it is minus infinity to plus infinity, right? But if you can limit the extent of the summation to n points and evaluate the continuous function of frequency at an equispaced point, just like we do the sampling, right? Take n equidistant points. Of course, here the x-axis would be frequency. Alright, so it is basically called the frequency domain sampling. So we basically sample the spectrum so that we get the spectrum which is discrete in nature. So that spectrum which has discrete in nature is known as DFT. So the basic fundamental difference between DTFT and DFT is that DTFT is continuous spectrum and DFT is the discrete spectrum, and it is mathematically defined as the equation. So the major difference that you observe is now the summation is not from minus infinity to plus infinity. We basically time limit the signal, say from 0 to n minus 1, right? And then you sample that signal. So your omega is replaced with 2 pi k by n basically. All right? Okay. And that can be seen here. Now, how basically DFT and DTFT are related. DFT is nothing but the sampled version of DTFT. Now to illustrate further, you can see here a DTFT is represented here. You see this? A DTFT is represented here. DTFT, right? So here we assumed x of n, a rectangular pulse. You see x of n is 1 from 0 to 2q and 0 otherwise. So it's basically rectangular pulse, and we all know that from signals and systems, we have all learned that the Fourier transform of a rectangular pulse is nothing but the sinc function, right? It is of some form sin x by x. We all have learned that. So remember, Fourier transform of a rectangular pulse is always a sinc function. Now you can see that here. Now what is a major problem with this DTFT? What is a major problem with this DTFT? It is continuous in nature. Do you observe that? It is continuous in nature. Such signals cannot be handled by the computer or the DSP processor. Now what we have to do here, we have to basically sample the signal so that you obtain a discretized version of this DTFT. That's all, students, the relation between DTFT and DFT. So to illustrate that, let me just quickly take you through. You can see here now, this is DTFT of a rectangular pulse, and then what we did, we took some samples. How many samples we took here? 22 samples, and then further we took 88 samples. So this DTFT is basically periodic in nature. This DTFT is basically periodic in nature. Okay. So what we can do, we can just take samples in one period. So here how many samples I'm taking? 22 samples in one period. Here I'm taking 88 samples one period. Concept is same, but what is the difference you see here? This is the more accurate representation of this signal. Could you see that? This is more accurate, but here, see, if you are asked to join something like this, right, it may not be the accurate, but see this is the actual representation. If you just draw this, you'll get very, very replica, very beautiful of the original signal. You see that, right? So the more samples you take, the better the resolution. That's a natural phenomena. So DFT is simply a sampling of the DTFT at spaced points along the frequency axis. Remember, it is all I mentioned earlier. It is a frequency domain sampling. Just like that, you do time domain sampling to convert a continuous time signal into a discrete time signal. You would also perform a continuous frequency spectrum to discrete frequency spectrum. Now, one important observation: what happens as n increases? What happens? The resolution increases. The sampling becomes finer, and therefore we get the true replica of the original spectrum. We don't lose much information, right? So DFT, DTFT is one and the same. Both are basically used to represent, give the frequency representation of time signal. But the major difference is that DTFT is continuous in nature and DFT is discrete in nature. DTFT, discrete time Fourier transform. All right. So let's quickly go through the problem. Right. So here x of n is 1, 2, 2, 1. So we all have seen the equation in the previous slide. This is the basic equation. Now you solve the numbers. You substitute n values 0 to n minus 1. Capital N is 4 here. We are going to perform a 4-point DFT. Right. You can find out those values. So you can see that it's mere substitution of to begin with n value followed by the k value. Now if we observe, this is your spectrum of the given signal, but it is discrete in nature. This is DFT. How many samples we have got? 4 samples. In the previous slide we discussed, the more samples, the better the resolution, right? So one thing you observe here, you observe a conjugate symmetry. At k equal to 1, you have minus 1 minus j. At k equal to 3, you have minus 1 minus plus j. So one important feature or property of DFT is that it exhibit conjugate symmetry, a very important property. That's what we are talking about here. The magnitude and phase functions are even and odd respectively due to the conjugate symmetry. And there has been given some mathematical proof here. All right, let's move further. There is this inverse DFT. Now, from the spectrum, we can get back the signal. This is the mathematical equation. And you also have some MATLAB code here, which can be explored further by you guys. If there are any doubts, we can discuss further. All right. Now, computation of the inverse DFT. right? So how do you compute inverse DFT? So x of k is given to you. You need to compute x of n. So we all know x of n is 1 by capital N, x of k, of course, summation x of k into e power j 2 pi kn by capital N. Remember here, capital N is the size of the DFT, right? I told you already the importance of capital N. And then you can, it's simple mathematical equation wherein you just keep substituting the small n and small k. Remember, small n represents time variable and k represents frequency variable in the context of DFT, right? Small n goes from 0 to capital N minus 1 and small k goes from 0 to capital N minus 1. So you vary those. Now you see that we got these values back when you were doing IDFT. You got this 1 back and then 2, right? And then 2, 1. You remember in the problem of DFT, we took 1, 2, 2, 1 and then we got these values, right? 6 minus 1 minus j, 0 minus 1 plus j, right? Now here, what we can do, one important thing is, we can plot the spectrum of this x of, how do you plot the spectrum? How do you plot x of k, the DFT of a given signal? It's complex in nature. So what we do here is, we take the magnitude spectrum, that is x of k, and then we take the angular spectrum, that is angle of x of k. So for example, you have minus 1 minus j, right? So you extract the magnitude, which is square root of 1 square plus 1 square, that will be root 2, right? And how do you find the angle? Tan inverse b by a. So minus 1 by minus 1. So what is the angle you get? Pi by 4, right? Degrees, or you can convert that into radians. Angle can be measured in degrees or radians. You see that? So for every point, for example, 6 is there, right? So 6 is 6 into e power j 0. Then minus 1 minus j is root 2 into e power j pi by 4. You see that point is located at an angle of pi by 4 with root 2 being the magnitude. Similarly, the next point would be is 0. This is 0. And then you get minus 1 plus j and then root 2. You get e power minus j pi by 4. You see, in the earlier we discussed, there is a symmetry here. Root 2, right? Even symmetry. But then you see here, this is pi by 4 and this is minus pi by 4. Do you see? You see the odd symmetry. That's what we discussed earlier. So DFT exhibits symmetry, conjugate symmetry. One of the important property which can help us further to reduce the number of operations. It exhibits conjugate symmetry. So magnitude spectrum will be even, phase spectrum will be odd. And how to compute magnitude and phase spectrum? It is pretty simple. Whenever you face a complex number, you take the magnitude square root of a square plus b square and then angle tan inverse b by a, assuming a plus ib is your complex number. Alright, so hope you understand what is the difference between DFT and DTFT and how they are related, and how we can basically compute the DFT of a given sequence, and subsequently the IDFT also, and also explore the property, the inherent property of this DFT, which can help us further solving a little complicated problems. All right. So let me summarize. So we discussed, so I've introduced the discrete Fourier transform as a truncated version of DFT. So we basically understood or discussed the relation between DFT and DTFT. What is the practical limitation of DTFT and how DFT can solve that issue. And also quickly we demonstrated how to compute the forward and inverse discrete Fourier transform. Hope this lecture session is of some help to you. If you have any doubts, please post it. I'll be happy to discuss.